All right, guys, so today I'm going to show you how to do specific heat of metals. I want to give you a little bit of background. Let me actually replay this really fast, reset this so you understand what we're doing here. So imagine I take a chunk of metal. Let's call it an unknown metal in this case. And so make it big, make it hot. And then imagine I take a liquid, typically water. So if you were in my class, you would actually do this. And so I have a hot metal, and I'm going to add a decent amount of mass here, and I have a cold water. So hot metal, cold water. So I'm going to mix these two things. So hopefully you understand that if I put a hot metal inside cold water, the hot metal is going to cool down and the cold water is going to warm up. Basically, the energy from the metal is going to transfer into the water. So the water will get more energy and the metal will lose its energy. So I'll just go ahead and run this in the background when we get everything all set up. So that's what's happening, adding the metal into the water here. So I've been talking about energy, and really that's because this process, we've got energy in the water and we've got energy in the metal. The metal is losing its energy. So think of it as negative energy. It's not negative energy, but it's losing its energy. And it should lose as much energy as the water gains. So if I'm putting a metal directly into this water and there's no outside influences, assume it's like a vacuum seal situation, then all the energy that was in the metal is going to go to the water. So this, let's say this loses 10 joules, this would gain 10 joules. This loses 100 joules, this would gain 100 joules. This equation is not the easiest equation to use though. So what we do, if you might remember this equation, Q equals mc delta T, we're going to plug in information from this into here. So instead of calling this Q of H2O, we're going to call it MC delta T of H2O. And on the other side, notice that I still have, I'm actually going to color it just so we really don't ignore that negative sign. Okay, instead of Q of metal, I'm going to say MC delta T of metal. And now I've got usable variables. So that's going to be super helpful. So now that I have these equations set up, and just to show you back here, one other thing, it's almost done. I think when I click off of it, it stops working. So remember, this thing started at 200 degrees Celsius. That was its initial temp. So I heated that metal on this hot plate and started this at 200 degrees Celsius. And then I had roughly room temperature water over here. And then I let the reaction occur. So I put the hot metal in the water. This is the end temperature. This is the final temperature, T final. It's the T final for the water and the T final for the metal. It's both of them because they're now one system. If you take an ice cube and you throw it in your hot tea, eventually those are going to reach thermal equilibrium. The ice will melt and the water will warm up to the same temperature as the tea. The tea's temperature will decrease a little bit and they'll be at thermal equilibrium. It's the same idea here. These are at thermal equilibrium. They both end at this temperature. So I recommend doing what I call a T-chart and having all the information for water on one side and all the information for metal on the other side. We're going to have to find an M. We're going to have to find a C. We're going to have a T initial and a T final, and we'll use that information to give us a delta T. I'm going to find all that information in an equation similar to the one I provided. So the one I made up is 250 grams of some metal is heated to 150 degrees Celsius. It's added to 500 grams of water at 25 degrees Celsius. So far I'm hearing masses and temperatures. Water's specific heat is 4.184 joules per gram degree Celsius. If the end temperature is 50 degrees, what is the specific heat of the metal? Blah, 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 blah. Let's turn this word problem into a non-word problem. So let's break down each number. This says 250 grams of a metal. Grams, we should know, is mass, okay? So 250 grams is mass, so it's going to be one of my M's. It literally says metal, so that means this is going to be my 250 grams here. That's my mass of my metal. Okay, I keep reading, is heated to 150 degrees Celsius. Notice that I'm still talking about the metal, so it belongs on the metal side. I see degrees Celsius, so it should have something to do with my temperatures. And this is actually our initial temperature. It's heated up to this before it goes through a reaction. So that was when we put it on the hot plate and heated it up to a super high temperature. That means it's actually its initial temperature. So 150 degrees Celsius for the initial temperature of the metal. It is added to 500 grams of water. Okay, it's telling us it's the water, so it's going to go on the water side. We should know that grams is mass. So 500 grams there. Cool. 500 grams of water at 25 degrees Celsius. That's telling you the water is starting at 25 degrees Celsius. Starting at means that that is its initial temperature for the water, 25 degrees Celsius. Okay, moving on to my next number, waters. So that's going to tell you it belongs on the water side. Specific heat is 4.184 joules per gram degree Celsius. Hopefully you're starting to get familiar that that is the specific heat capacity, the C there. Also, if it helps you, C equals 3. There's 3 units, joules, grams, Celsius. C equals 3, so the 4.184 of water, because it tells me it's 4.184 joules per gram degree Celsius. Cool, I'm starting to dissect this problem, making it not a word problem. If the end temperature is 50 degrees Celsius, that's the next part. If the end temperature is 50 degrees Celsius, remember that's the final temperature for both things. They are a system now, okay? They are a system now. So they're a system now. So that means that the end temperature is the same for both of them. So same would apply in this scenario. If it says the end temperature is 50 degrees Celsius, that has to be the 50 degrees here and the 50 degrees here. It's the end temperature for both of them. Lastly, it says, what is the specific heat of the metal? That means that this is my question mark, or this is my students like X, so I'll do X in that one. That's my X, that's my unknown. I should have everything else besides the X, okay? But I don't quite have my chart filled out. I need to remember that delta T is T final minus T initial. So in this case, T final minus T initial, 50 minus 25 gives me 25 degrees Celsius for my temperature change. And over here, T final minus T initial. And that's negative 100. 50 minus 150 is going to give me negative 100. That negative is important. Remember, the metal cools down and the water heats up. And we saw that in the little simulation. Now I have everything I need. Now all I have to do is plug it into my equation here. So MCT of water equals negative MCT of metal. I'm just plugging numbers in. So my M of water is 500 grams. I'm going to leave the units out just for saving space. Times my C of water, 4.184. Times my delta T of water, 25. That's everything on the left side. Equals negative. In fact, let me go ahead and keep that with our color change there so we're really clear. Negative, I need an M of metal, 250. Times my C of metal, which is my X. Or you can leave it as question mark, or you can leave it as the C value, whatever you want. Times my delta T of the metal, down here, negative 100 degrees. And now I'm ready to do my math, all right? Don't overthink the math. Let's simplify the left side first. So 500 times 4.184 times 25. Okay, so just so you can see my proof, 52,300 on this side. All right, on the other side, I basically have a negative 1 in front here. So negative 1 times 250 gives me negative 250. And then I have negative 250 times a negative 100. Hopefully, we are aware that a negative times a negative gives us a positive. So those numbers cancel out. So really, it's just 250 times 100, which gives us 25,000 still times our X. When in doubt, do the opposite. This means 25,000 times X. The opposite of times or multiply is divide. So I'm going to divide both sides by that number. So I'm left with X alone over here. And then just do my division there. So 52,300 divided by 25,000 gives you 2.092. The units are joules per gram degree Celsius. For my class, for my purposes, the examples I'm giving you are going to be this exact same setup. We're going to continue to find C for the metal. We're going to continue to just have to find from the word problem all these other things and then plug into this equation. That's how you do specific heat of metals. Thanks.